So can anyone tell us the kind of the mathematics behind, or the mathematical concept behind XGBoost or boosting? What does it mean, boosting? So we have 3 ensemble methodologies: stacking, boosting, and bagging. Can someone try to explain their understanding, how they differ?
Hi, can I try?
Yeah, Abubakar, go on.
Yeah, so for boosting, what I understand about boosting is it combines weak learners, like it trains on some parts of, it trains on all the part of the data while using simple processes. So it builds weak learners. So for the part of them boosting, it combines all the weak learners and try to adjust their mistakes with the other algorithm. So it just combines all the experiences of the weak learners to generate a good result. That's what I understand about the boosting.
The boosting, okay. Great, yeah. So can anyone shed a little bit more light? So these are all, so there are 2 things. There's nothing that is algorithm that is not mathematical in some way, because you can't build as a mathematician, as a statistician or a mathematician, you always build some kind of optimal, so either greedy methods or optimal methods. So you somehow have to write them down, and either you write them as sets or you write them as functions, and you try to optimize on that. So who didn't take any mathematical course in the university? Just so that I know. So put your hands or do something if you haven't taken any mathematical course.
It's been a while. Grade level. Yeah,
Sure,
calculus.
but at least you have taken some courses. Yeah. And optimization, who has taken optimization?
So I don't think
course?
I understand what optimization course means.
An optimization course is like a course that you specifically studied some kind of optimization methods, like a mathematical course. I think hopefully most people didn't, and that's fine. And who has done numerical methods in university? So using, for example, taking Python or MATLAB or anything else to do derivatives, write their own function on derivatives, estimate functions, like some kind of like differential equations. Okay, yeah, that's definitely, I did have also some kind of, depending on the teacher, optimization can be the worst thing you have taken or the best thing you have taken. So okay, I am missing a lot of sorry. Sorry, just one moment. Okay, so yeah, but I need a refresher. Definitely doesn't concentrate in count. I have done optimization, but mainly on paper. Wow. Can you tell us what is? I think that's good, Ratomi.
Mainly what I did was on operation research, but I've done on operation research, I've done, okay. Let me recall and jot everything down, then I can say it.
No, it's okay. I know it was not. I know that sometimes it's hotspot, but I mean, the one point that I want to understand is that it is good. Like it is. I think I was in optimization when I did just was elective course. I was even doing maths and physics at the university, and then I took optimization because it looks cool. And then, but the teacher was really bad, so bad that it was the only grade I have. I think I had D in my ever life. I mean, in my university life, I didn't have D except that one, and that was because just I hated the person, right? So sometimes it's really the nightmare is because of just how you studied it, and when you actually apply it in a certain way, and don't get afraid of it. Just it's really, it's not that in all your life you do it. It's just a matter of formalizing it, right? And in the mathematics, always try to just not only read text-based or graph-based blogs, read a blog that has at least mathematical equations. Otherwise, you get really, I can't see. I mean, I'm thinking about ladders in your career. This is a junior position, that's great, right? But then to go up in the ladder, you really need to understand papers, mathematical equations, and also the word behind. So let's talk now about the boosting, bagging, and stacking, right? So we can definitely, I think what Abu Bakr described is really correct. There's no, but what does it tell you? Like, so is there anyone who can attempt to try to relate it with some kind of, so does anyone understand how trees work, random forest work? So who can just tell me about what is a tree algorithm and what is the random forest and
I
what
understand.
is, yeah, go on.
I said I
Go on, Abu.
understood how decision tree works. I understand how decision tree works.
Yeah, okay, so decision trees, yeah, exactly.
So from my understanding, yeah, what it does is it splits all the features into different branches, and then it tries to arrive at the conclusion at the last part. So if for example we have like 4 features to predict or to say if someone will deposit into a bank, so we have age, marital status, and some other stuff. So what it does is it groups them. So if the age is within 30 to 40 and then the marital status is married, then there's another yes or no to answer that part to say, okay, yes, he probably will deposit. Then it will check another feature to answer that similar question. So if that feature says a particular value, then it goes down the tree until it reaches the max depth to now finally conclude that, okay, this client or this customer will deposit or he or she will not deposit.
So how would you write the equation if you were tried the decision tree?
I think it will mostly evolve around if and else statement.
No, in mathematics, not, I mean, true, but how would you write it? With variables, like what kind of equations would you write?
Okay. I don't know. I don't know.
No, I think I think when you see it, of course, you might say, oh, of course. So maybe Elvis, just given your theoretical understanding, some things like, what would be like the kind of equation would you write?
Hey, Yabi, I need to arrange my thoughts on that subject.
Yeah,
it's been
sure.
long before I.
No, it's fine. So it's basically you would write it as a set, right? So because what you have is just values, right? Just like if you have trees, on each of the tree a branch, yeah. So where there is, so it's kind of, yeah, there will be a main tree, which basically you select, and so you will have a boundary. So it's kind of a boundary. So depending on if it's just a single feature, right? So you will basically associate X to be the feature, and X will be an array, and then you will have associated to it will be just a boundary, like, which is just a value, and then like that, kind of like, and then it could be a set of elements which contains the feature and its boundary. And basically, finally, it's going to be a set, a huge set, where that's just your tree, right? So it's how you represent a graph, is basically how you represent the how you represent the equation. Okay, so boosting is so I'm going to go through this paper. Hello.
Yeah, please, can you go over the boundary stuff in the decision tree?
So what I was saying is that you will basically how a data is structured, graph data is structured or saved in a computer. That usually will be the kind of the node, or in this case would be the feature, and then the split, right? So that means this, like, as if it's height, like for example, one of the feature, so there would be like, of course, the feature would be height, and then the value of that boundary would be call it beta, and that would be like, okay, 1.6 meter, right? And that would be just one element, and then there will be another element. So those becomes the form of nodes, and it could be structured as list of lists. So that's what's and that's what you will represent it also in a mathematical, just basically a tuple, and then you will continue. So, and this you can
excuse me, yeah.
Yeah.
So if I understand what you explained very well, is that okay, a decision tree, if you want to write it in a mathematical form, is going to be something like writing a set, right?
It's a writing a set, exactly.
Okay, all right, thank you.
It's a writing a set, but it can be, there are many ways you can write it as a function. So h of x, so I'm gonna go through that. So it's just before I project that I wanted to talk about this thing, so that you don't get, I don't know, some people might not like to see equations. But I'm gonna, because this is the kind of, sometimes you need to read this kind of, I mean, I will share this paper, but this is the kind of an idea about gradient boosting. And so if you, when you read it, it's basically in this function estimate is, so I'm gonna, so usually, so in this predictive learning problem, you have a system of consisting random output, which usually we call it a label, right? And a set or random input or an explanatory variable that are considered as your features. So in our case, y, like in the case that we are solving, would be y are just the set of elements that a person has or a customer has, the insurance package, and then x are its age, or how, when it came, you know, when it was registered, or stuff like, so number of features, right? And then whenever we want to put this thing into a mathematical equation, we set them through this set equation that basically is an ordered set of x, yi, xi. This is basically the features, and this is the labels. This I represents basically just a single observation or an experiment, and then there are n number of data points. So usually just a single point is already enough. It's a data, right? So these are then a series of them, and that's why we use this kind of notation. And or if you want to represent, instead of this 1n, you can actually make it y to be just another vector, x to be a matrix. So in this case, y is your vector label metric, your label vector, and x is just your feature matrix. So that's usually how whether it's deep learning, machine learning, usually we start. We sometimes can reverse X, Y, but it just doesn't matter, okay? And then the goal usually in machine learning is to get an estimate of or an approximation to a certain unknown function, because you assume that there will be a function, which is the world in this case. If it's a picture, it's a camera. If it is a record, like in tabular data, this would be basically what, when you imagine just you have like infinite set of record for something, then if you plot it, that is basically just like if you plot each of them by transforming it into some kind of numbers, and then plot the value, that means the label, as a coordinate. It could be just the axis basically becomes a dimension. And then in that, let's say if you have three variable or three features, then it basically becomes a three-dimensional plot. And then how the plot look like, or that thing is called f. And that basically assigns for each of the coordinate points, f in this case, for each of the coordinate points or the features, assigns a value. So in this case, we call it f of x, but that is its true instance. If you call it a class, in one of the instance, it gets y, right? So that's basically what we know now at hand is y. But of course, y is kind of like, it may not be a one-to-one mapping. That basically could have a noise. If there is a noise, then there could basically y is related to f with plus noise. So usually that's what we write. Y is equal to f of x plus some kind of noise, okay? But if there's no noise, then that basically relation is y is equal to f of x. But
hello, sir, please.
Yeah?
Please, I don't understand the concept of noise, sir. Please, I don't know what
okay,
noise.
so noise in any engineering or system, it's basically when you do an experiment. Let's say you are taking a camera and you're taking a picture, the actual pixels of the person you are taking the face, the brightness of that point in the person's face, for example, is the signal. But then as the light propagates to the camera, it is deformed by the air. There could be, for example, a dust in the lens, and then it goes in, and then there will be a noise in how it's then translated into a pixel, right? Just the intensity of light. So now the value y, whenever we say y is the pixel value, just what the final picture value. F is actually what you're really measuring is the one on the face of the person. So, and anything else between the face of the person and the pixel that you are observing, any difference between them are a noise. But that noise is very different for each of the pixels. That's why it's usually noise. And it's kind of Gaussian noise or random noise, or white noise means this thing is random, just randomly fluctuating. If you take twice a picture on the same spot, you get a different noise. Is that clear? So it is the same thing.
Okay, what I understand from, like, what I understand now is like noise is something that is not what we need. Like it's not useful. That is what I'm saying.
Of course,
like,
it's
not correlating with what we have, like what
absolutely,
we are supposed to have.
Absolutely. That's why we usually put it as f, and then if we take the correlation between the signal and the noise, it should be 0. So that's why we usually have like, separating. So noise is uncorrelated almost always. If it's correlated, it's so complicated, but we most of the time assume it's uncorrelated because it's different. For if you take the same picture twice, you should get different. If that is not the case, then it's not a noise, it's called another signal. So which is then again kind of summed as another quantity, but not as a noise. But usually noise is just this random one. Like that's the case. Okay. But this f that relates the camera, the person, the face, the pixel, the point in the person's face, and the pixel, that is unknown. We have no idea. It's really complicated, right? If you want to model it from a physical perspective, that requires knowing how light propagates. And imagine if it is about record, like in a bookkeeping record or an insurance record, how it relates the person's name and to the person's insurance value is basically a voodoo. We have no idea how a person's name relates. But given that it's not just only a person's name, but it's a person's name, its age, its other properties, where they live and stuff, then you might assume there is actually some information encoded. If a person is rich, for example, and they have a lot of money and they're old, you know, you're most likely that they probably will want insurance of a certain form. So that is information. So the only thing is that this F is trying to capture that kind of information. So that information. Sometimes if that information is not, if it's random, when we say random, F means just noise. That means there is no correlation between them. So F is a form that we're trying to find, but we don't know F. There could be anything. So that's why in optimization, when we are trying to find what the form of F, the easy way is like let's assume F and then calculate it. And then let's then take some kind of derivative on that space and go on and go on and go on, collect as many F possible as much as possible. And then let's take the best F, which is usually denoted by star, that maps that when you take the loss function, which is for example, the mean square root, then it is a minima. And that is what this equation is saying. It's saying the arg minimum of F. So the minimum F, when we take the expectation over a loss function of y and f of x, and given y and x, f is unknown, you're just varying, then the minimum of that, let's call it f star. So this is how you write basically the whole optimization in one equation. So this is just the optimization line. This is the central line of every optimization you're doing in machine learning, right? It's deep learning, it's everything, right? Everything is just that, what in machine learning you're trying to do. And then you can rewrite it instead of AYX. Of course, you can also, if they are separable, that means like the label.
Hello.
Yeah. Anyone with a question or? Okay.
Yes, there's a question.
Yeah.
Can you hear me?
Yeah.
Okay, basically, so what you're saying now is that this F asterisk, what we
Yeah.
are basically doing is just to find the minimum value of the loss function, right?
The F that gives, remember this equation saying the F that gives the minimum value of the loss function. Yes.
Loss function that is giving the y
F star is
value, that is
an
predicted
F
value, and
an F value. So this basically this part is really saying it's arg mean. So it's not, if it's just mean only, then you are saying the minimum value of the loss function. No, in this case, the arg mean of F. So that means the F that gives us a low minima, a low loss function, or a small low expected. So this E is expected. That means when you are summing over, because it's not just 1 point, but when you are summing it over, that's expectation. The F value that gives the smallest loss function is that we call it F star. It's just a naming. It's like, you know, a person with a red shirt and has a height of 1.8 meters, and he's from Nigeria and blah, blah, blah. Let's call that person F star. So it's like specifying what that is. So always it's about naming. In mathematics, it's about you name it. If you name it, then you can go on. Is that clear?
okay, yeah, very clear. So now another question is this: for this F now, this F star is the arg minimum value, right? Okay, so basically now if it's in linear regression now, and you know, in
There's
linear
no
regression
such
is
thing,
just
linear
nx.
regression. What?
No,
There's no such thing, regression.
No, I'm talking about, let's say, I'm just giving an instance. If
Okay.
you're using linear regression, let's say we are using linear regression and
Okay.
it's mx plus c. So basically the weight values is just the m and then the intercept, right? So that means this f now might name this f m, right? That means
Sure.
this m that is giving us the minimum value for the loss function.
Sure.
Am I right? Okay.
Yeah,
Thank
absolutely.
you very much.
Yeah,
Thank you very
that's
much.
exactly the case. So yeah, this is a general application in that simplest case. Thank you. That's exactly that. But instead of thinking of that, think of f, in this case, because it's written as a function, you are writing y is equal to f of x, but f of x becomes, this is not a parameter, this is a function. So in this case, basically, yes, it's kind of estimating its will come later. This f star is parameterized by, in this case, m in your equation, m and c. So mx plus c. So this f star is kind of made up of this value exactly. Just but it's going to be a set basically, or a tuple in that case, because this is a function, because we are writing that linear function mx plus c as f of x. So that f in this case basically becomes that. But yeah, it's the same. It's just knowing clearly is okay. So I will continue because we're because of time, and I think and we need to get somewhere. So now the frequently employed loss functions for this case. So this is a loss function. All right, so we can write it like that. Sometimes we can just take out the x just once we know f is a function. And the usual loss function is the error function, the square error. That's what you know, the mean square error, right? Or the absolute error. That is basically when you have what you call, this is called L1, this is called L2. So every time when you hear like some kind of L1 regularization, L2 regularization, what really means is just L1 means something, its difference is square. L1 means its difference is absolute valued, okay? And when y is an element of a continuous variable, when the label is continuous, then it's regression. And we usually use then a negative binomial log likelihood when the case is classification. For example, if it's -1 and 1, when the label is just some kind of like, apple and orange or cat, whatever. Just when it's just only discrete, we call it, when it's discrete, we call it classification. When it's a continuous or a real value, then we call it regression. And for regression, usually we use some kind of mean square error because it makes sense, it's a distance, while for some kind of classification, we use binomial log likelihood or anything that you know, right? Okay. But the usual way to estimate f star is actually as just Lucra said exactly, f is just a function, we just call it f, but that we can parameterize it as linear. In that case, if we parameterize it as linear, then it will have its own parameters. In a linear case, it will be the slope and the intercept, mn. And that's what usually then you can write f of x to be more like f of x with some of its parameters. And those parameters are p1, p2, whatever. It's kind of a finite set. So a linear case would be just, in our case, this is slope, and this is just the intercept. But you can assume it could be a quadratic function. In that case, there would be 3. It could be a polynomial.
Yeah. I don't think we can see your presentation again. I can't.
Oh, don't you see it? Or is it?
It's only you, Lawal.
I can see it.
Oh, I
We
can
can
now.
see it.
Oh, sorry.
Yeah. Okay. So do you see it, Combo? Just maybe if that's.
Yeah.
Do you see it now? Okay.
We can see it.
I can see it.
So great. So this is basically p is in that case p1, p2, whatever. It's basically just your parameterization. If it's a deep learning, you know what that is? Who can tell me what this is if it's a deep learning? What is p if it's a deep learning, if it's not a linear function? A linear function.
Sorry, can I try? I don't know. I might be wrong.
Go on. Wow, I can't hear you. Huh?
Yeah, activation function.
Sure. I think your background is clear, but let's just stop it, please. Can you pause it? It's too okay. So maybe type it and someone can read it. That's too noisy. So P basically, just for the sake of time, it's basically your weights. So these basically are all the weights and whatever function that describes the some kind of the convolution everything else, basically all the parameters that defines the.
Sir, sorry to.
Yeah, go on.
You did not talk about the E. You talked about only F. I don't know. Did you talk
No,
about the E?
is
Yes, E and F.
expectation. Is expectation. Expectation means the sum. It's batch. In this case, when you do batching, that's basically that you sum over the batch. So it's basically you sum over the data point or anything. It's an expectation, but it's an integral. So if it's discrete, so E is basically an expectation. You know, expectation means usually you're not estimating at using one data point. So if it's an image, you use a lot of images to estimate this value. If it is, for example, a linear function, you have many dots in your plot in XY. So all of this XY represent, you have to sum together to get a parameter value. So that sum is called expectation or integral. So E stands for expectation or integral. They are the same. They mean the same thing. They are just sum. Is that clear, Emmanuel, or still confused?
No, sir. Like, what are they summing? I don't understand. What like, please just let us. Like, I need something I can see. I cannot imagine what he is summing. Please.
Okay. So I think for the sake of time, I will continue because the plan today is just to go through. Definitely, I know that some people may not see, but may have a more visual mind. And it's mathematics is not some, but it's like variable, just summation is, I think in this tutorial, what I want is just to take you through words and I'm going to follow, but then you can, of course, go and just write it a note and say, just kind of, you can go like, okay, like there are definitely a lot of, I will send some visualizations where like some animations that will show this kind of things. But the goal of this is just to go through the mathematical part, okay? So just follow it, and then later you will have kind of like some visualizations that you might see. But yeah, I know that this is not for everyone. I'm sorry, but just we need to go through this such that we can relate how to write a mathematical equation for some of these like the machine learning algorithms. So just let me continue, but I know, I'm sorry if something is very not clear. And yeah, and you have in 10 minutes or 20 minutes, you have also Idris. So just let me go through. So basically just this piece are in deep learning, this will be the weights. In linear function, this would be just the slope and the thing. And in kind of like tree, like decision trees, these are basically your boundaries for each of the trees, like for each of the kind of the features. So that's exactly what I was saying. You can write the tree as kind of like that. But in this case, P1 becomes a tuple, which is the feature and its value, right? So with that kind of thing, the whole type of equation can be parameterized then with this kind of equation. So basically you're saying to write the whole tree, what do? I need the feature. I need how that feature is related to the label. And then I can parameterize it by a tree. So this is a tree in my case. And each of the tree I can weight. So when I'm weighting the trees, then this becomes a random forest. So this is basically each of these are tree. It represents a tree because it's X and some of the tree parameters, like the kind of the boundaries for each node. And then this becomes the weight, and the sum becomes a random forest or anything that you can ensemble method. And this is exactly what earlier Abu Bakr was saying, that this is just a weak learner. So now you are combining a weak learner and you form some big function. Okay. So the generic function hx is usually a simple parameterized function of the input variable. By a is basically that. The individual terms differ, whatever, so you can read it. And such expansion at the heart of many function approximation methods are neural networks, radial basis functions, Mars, wavelets, support vector machines, decision trees, random forests, XGBoost. Everything is kind of really, and for a regression tree, so this is exactly for a regression tree, which is a decision tree, the parameter aim are the splitting variables and splitting locations and the terminal node. Like, so basically you can read it. So that's basically what you are trying to do. And what you are usually learning is that this aim, and when you are constructing ensembles, this is BM.
Hello.
Yeah.
Please, can you go over the last equation?
This one?
Yes, just a brief overview of it, please.
So, okay. So this HXM, basically, it can be anything. This is basically, this is basically your features, and this becomes, for example, if H of X, if you want it to be a decision tree, basically aim represents your splitting values. So for each of the splitting values, and X represents basically your features. For that X, the splitting value kind of, and as a function, this function will give you just basically for all of this at splitting at nodes, the values, right? So that's basically what you will write mathematically a decision tree. And
okay.
Yeah, I think your background. It's so hard. I'm sorry, but if you can't type it and other people can say it, then I can answer. So, and then basically the parameters that get in the model are BM and aim. They are the ones we are trying to estimate. And so basically that's basically, if it's a linear function, you know, consider it, this is a multi-line. So it's not just one line, but multiple line. Then BM becomes the weight of each of those lines, and aim basically becomes your slope. So this basically is a vector which contains the slope and intercept. Okay. Okay. And then numerical optimization. That's basically, as I said, P is just basically like that, and F is now parameterized that way, like this, with this equation. And then basically what you're trying to find is the F that gives the minimum loss, that we just talked about it, but by breaking it down like these three, which is like, okay, I am going to find P's, which are the parameters that gives me a very small function, I mean, a small values, the argmin, who's basically just, this is how I am going to write it. That basically the expectation of the loss is what I call it phi of P. And then basically F star is basically just the P star. So the P star, which gave the minimum value of the loss, is what I consider F star. And then, you know, basically at each point, you kind of sample them. It's heuristic. It could be MCMC. It could be any other optimization. It could be gradient descent, stochastic gradient descent. All of that is trying to find the set of P's. So kind of at each point, it gives you one suggestion. You start from somewhere, and then they kind of go and kind of build this chain, basically. So MCMC builds what you exactly built in week 4. That basically just the parameter values at each step basically becomes your P values, and the distribution, the peak of that distribution becomes P star. Okay. So, and the steepest descent is basically, again, after this, it's just a matter of like, I know it's slightly complicated, but after this, you are really just doing what you're trying to do is that, okay, I want to estimate the gradient at each of this point such that I can go to the lowest point, because I'm minimizing my loss function, right? So I'm taking the derivative, and I'm taking the derivative of that, and then I'm taking the minimum of that to be basically just, it's here, the minimum of that. So the minimum, so the negative of the gradient to go to take the next sample. So that's basically, an MCMC would be just another sample in your like whatever proposal you have, how you go to the next point, from the point you are in to go to the next point. Gradient descent basically uses the derivative value at that point. And I will send another animation how you could, you know, like you visualize this thing, basically this whole point. And then you form basically, so in optimization, usually we are not interested in each of the sample. It's about going to getting the minimum. While in MCMC, you store everything. So that's the difference. So now, whenever we say like kind of the learning rate, what we are saying is that we estimate this gradient descent, like with derivative, but we are multiplying it by a value. So let's say the derivative is 0.1 at that point. Now you can multiply it by some value called eta, that is kind of the learning rate. So whenever we say learning rate, it means it is in this trying to find p, the lowest, the p that gives you the lowest loss function, you are actually multiplying the derivative by a certain value. And that is called the learning rate. If you take the learning rate high, that means if the derivative is like 0.1, and if the learning rate is 1, you really are going like, no, by 0.1, you're kind of going really faster, right? So that's what this kind of learning rate is. And in the XGBoost, when you are optimizing, the kind of the depths of the tree and all that means you are actually optimizing here. The hyperparameters that are here, the depths, whatever, is controlling this parameter. And how they are sampled and how they are weighted, when you are fine-tuning that, you are fine-tuning the weight function, the weight that sums different trees or the different weak learners. So then after that is really just a simple kind of whatever. Then this is how you do it in finite data. I think I mean, because of time, I won't go through, but basically you're really doing now when it's a data instead of now function, that's how you do it. X becomes xi because it's a sample, a data, and then you basically just do exactly, but you try to find this BM and AM, the weights, and then the three splitting points, and that basically becomes a model. So your model basically becomes these values, right? So just finding this, just like MCMC, it's finding those parameter values, but those parameter values are, you don't see them, but in MCMC already in week 4, you saw those parameter values. They were lambda, they were beta, they were mu, which but in this case, it's basically how splitting functions of the splitting values of the tree. So I think then we go through, and basically that's how then the algorithm works, gradient boost. And then basically you can have the least square regression, or you have a lot of like, when it's a regression trees, you basically have like boosting, tree boost, and other boosts, different types of XGBoost and all that. Okay, so but I'm not gonna go through that. So I know it's a lot. This is just more to show you what it is, but then I will go to exactly the code, which is just usually the easier one, right? So this is a decision tree, right? So whenever you say this yes or no, this is what you call a splitting. When a tree, just a node is split, so you split it here. So if this was a binary split, but it could be just a regression, and the regression means this would be like a height greater than 10. Yes, it goes there, and whatever. So that 10 basically becomes what earlier we call it A. Just that value, just that you use to compare, to split, is called A, or the subset of them, basically, right? So when fine-tuning, this is in your reference. There are many things you need to optimize. So one is tuning the number of boosting rounds. So earlier I said the boosting round really just means the number of times you calculate the derivative, gradient boost. So earlier I said it's kind of in the MCMC case in week 4, that's the number of samples. So the boosting round in XGBoost is basically the number of kind of gradients that you're computing. Okay, so that's just exactly the same as when you were trying to minimize computing time, you were playing with that number, draw, like, or some kind of n whatever. I forgot what that is in MCMC. That's basically the same as. So the number of boosting rounds means exactly you're kind of giving it 5, 10, 15. So it kind of basically you are doing exactly samples, computing the samples, right? And then early stopping is really nothing, but what you are saying is that, okay, when should I stop? So you could, instead of stopping by like this one, which is the number of times you would sample, you could also stop when the improvement in the kind of the derivative or the value that you get, which is the loss change, the change in the loss function when that is smaller than a certain threshold. So it's kind of, and then that is called early stopping. If the loss function at each of iteration doesn't change by more than a certain amount, then you call it a stop. So that's called early stopping. So that's what's kind of, you just basically early stopping 10 in this case means if the change in the loss function is less than 10, stop. So if you see the output, then this is basically in the test. So this is basically in the test. So it was first changing by a huge amount, 58, 29, 32, 12, 20. Now this was, the improvement was just only about 8 point something. So then it stops there. So that's what's early stopping. And another part, so this was all on the derivative part. So this early stopping, sampling earlier, what we call boosting grounds or early stopping are on the derivative, on the number of samples and all that, while these parts are on the tree, the learning, again, learning rate is on the derivative, but some of that are on the tree, which is basically the maximum depths, the subsample, and the call sample by tree. That means the number of columns that you sample for each of the tree. So, and these are all just other L1 regression on leaf weight. That's basically just when you take the absolute L1, as I said, is the absolute value of just that leaf weights, and then L2 is basically just some kind of error function on the lambda, on the leaf weights, right? So basically just this describes the number of ways you do tuning eta, which is basically the learning rate, tuning maximum depths. This is just on H, when we just talked about H, which is just the tree depths, how much you split, in terms of like, if it is small, that means it's a shallow tree. If it is big, then it's a very deep tree. And then you have grid search versus random search. So grid search, basically, you have now eta, all other parameters. You can search, you can go through step by step on them, or you can do some kind of MCMC sampling on them. So random search means basically sample randomly. Grid means iterate on each of these parameters and sample regularly. So this is very expensive. This is, you control how expensive it gets, just like I think. So with that, I know I have been a lot, but I will stop here. And any questions you have, just I will, for the next 2 minutes, I think we have 2 minutes before you go to the next one. Okay, anything? Was that useful? If it's not useful, sorry for wasting your time, but I'm sure you will find it useful at some point, if it was too much. But it's always good to look at just how this is represented in maths, and then what you do, it's kind of, is really means, you know, what does it mean, this learning parameter? What does it mean this? What does it mean that? What does it mean boosting? Boosting is basically just that, the kind of the derivatives you're taking on the tree. So it's kind of, I will share with you the paper. You may now, when you read it, it might get easier on yourself. But at least now, when you fine tune, you know what you are fine tuning, hopefully. Okay. Seems we are running out of time, so let's stop here, and we can talk over Slack. Thanks. Cheers, guys.